Today we are going to discuss all pairs shortest paths, though we have discussed it before, but today I will give the summary of the previous lecture and then we will continue with the same topic. Let's start off with the proper formulation of this problem. So let's say we want to formulating all pairs shortest paths. So in this case, formal definition of it is let n is equals to the number of vertices and all the vertices are arbitrarily labeled with 1, 2, 3, so on up till n. All, then if this is the case, then all pairs shortest path algorithm is represented by n cross n matrix, or you can say n cross n distance matrix. Let's represent it with capital D. Then D is equals to Dij, where Dij is the shortest path between I and j, which is equals to the weight of the shortest path from I to j, provided if a path exists. Otherwise it is infinity if no path exists, right? So this is how your n by n matrix is defined, and along with this matrix we will define another matrix. Together there is another matrix of same dimension n by n, matrix n by n. Let's define it with the capital Pi, which has pi ij entries, where pi ij is equals to either nil or predecessor of j in our shortest path from I to j. This is in the condition for nil is if I is equals to j, that means we are going back to the same vertex. For starting and ending vertices are same. If that is the condition, or there is another or, there is no path from I to j. So that means the predecessor or the predecessor of j in case of I is equals to j will be nil. That means we are going back to the same vertex. There is no predecessor. Or the second case is if there is no path which is taking you from I to j, that means that there is no predecessor of j, because again we are not connected, or there is no path between I to j. And if first one is if his condition is false, for all other cases we will have some vertex I which is the predecessor of j. So these are the two matrices which we are representing. First will represent the shortest path and the other one will represent the parent node. So remember that if you only want to calculate the shortest path between I to j, this matrix is enough. D, capital D is enough. But if you want to construct the complete shortest path between I to j, in this case you need to have this pi matrix. So in this case what happens, so you will start from the very end, let's say whatever is this j, then you will move towards its predecessor which can be read from this pi matrix, and let's say it is some node over here, then the predecessor of this node will be read from this again matrix, and we will continue going backwards towards the starting node which is I in this case, and the whole shortest path will be calculated, and the overall Ij will be the entry Dij which is stored over here. So hopefully this is clear now. So keeping this discussion in mind, so this means that thus the ith row of this capital pi represents the single source shortest paths starting from vertex I and ith row of capital D matrix gives the weights of these paths. We can okay, we can define another weight matrix. Let's define another weight matrix W which has Wij's, where Wij is equals to weight of edge Ij, of course if edge exists, otherwise it will be infinity if there is no edge between I to j. Okay, you have to differentiate between capital D and capital W. In this case we are talking about the edge. If there is a direct edge between I to j, then the weight of the edge will be represented by wij, otherwise all and other values will be infinity. So we are talking about direct link between I to j. If there is one, then it will be represented by w. So remember that the original given graph G is a digraph or directed graph. Therefore, the matrices D, capital Pi and capital W are not necessarily symmetric, right? So the existence of path from I to j does not tell us anything about the existence of a path from j to I. So keep that in mind, it is a digraph, so that means it is directional. So if we have a path from I to j, it is not necessary we have a path in the opposite direction. So as we mentioned before, so in case of each row, if you have already studied single source shortest path. So if we have, let's say, pi graph, so in this case this represents I, and we have a value over here, over here, over here, over here, so on up till n, right? So whatever is the ith vertex, so that means we are talking about a single source shortest path with I vertex, this one I, y as a source node. So all other nodes 1, 2, 3, 4 dot 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 up till n. So what we are trying to do is, if in this case I is equals to 1, then in this case first node, whatever arbitrarily labeled node 1, will be taken as a source, and we will calculate the shortest path between the nodes. So in this case, each row represents a single source shortest path with ith node taken as a source. So there is a very close link between this problem and the all pairs shortest path. Okay, this is the formal definition of a all pair shortest path. So we have to calculate d capital Pi to find out the shortest path. Okay, so in this case, question is how we can do that. So for that, there is a very good approach. Let's start off with a very simple approach. We have studied Bellman-Ford algorithm, and Bellman-Ford algorithm solves or finds the shortest paths between I to j, right? Or I is your source node. It also handles negative weights and negative weight cycles. So In this case, what I can do is I can apply Bellman-Ford for this first row and using ith node as my source and find the shortest path between first node 1 and all the subsequent nodes. So in this case, this problem will be solved for me. Or we can say that there is a negative weight cycle in this row and I cannot find the shortest path in this particular row, and this will be reported by Bellman-Ford because Bellman-Ford reports the negative weight cycle. So similarly, I will perform the very same thing for this row, then this row, and so on up till n. So you can see that I have applied Bellman-Ford n times. So in this case, n times Bellman-Ford will be run. So if we know the time complexity of Bellman-Ford, then in this case what we can do is we can just have to multiply it with n. So okay, time complexity of Bellman-Ford is equals to big O of VE. This is single source shortest path. If we have to run it for all the vertices like we have talked about over here, so for all pairs shortest paths, Bellman-Ford algorithm will take V multiplied by big O of VE time, which is same as big O of V square E time. But remember, in dense graph, number of edges is roughly is equals to the V square. That means each node is connected with every other node. So in this case, altogether excuse me, altogether we will get the number of edges almost equals to V square. So by applying or by plugging this value in this equation, we'll get that Bellman-Ford will, in case of dense graph, will take almost V raised to power 4 to solve all pairs shortest path. This is what we have discussed before, and we'll continue from here onwards. So it means that we have to improve upon it. So then the second approach which we can use to improve upon dynamic programming approach, there will be at least two approaches which we'll be discussing today, which involves dynamic programming. Okay, first one is simpler one. In this case, what we are saying is we will build our path incrementally. Okay, so let's say I have a starting node I and I want to go to J, some node J. Initially, I say that okay, I am not allowing any edge to be added and I want to find the shortest path between I to J. So that means what? I am not allowed to use any edge between I to J. Then in this case, what is the shortest path between I to J without using any edge between I to J? It should be infinity if I is not is equals to J. That means I cannot go from I to J because there is no edge allowed between I to J. But at the same time, this can be is equals to 0 if I is equals to J. That means if I have to go back from I to I, that means J is equals to I. Then in this case, I do not need any more edge. Rather, I am already there in the in vertex I. So I can straight away say that I do not need to use any edge, and in this case the shortest path between I to I is 0. So these are the two base cases if I am building my path. Okay, then okay, in the next iteration I'll say okay, That was when your allowed at most number m represents the most number of edges allowed between I to j. Okay, so in this case when m represents that, so when m is equals to 0, this is the case. Okay, incrementally we'll say that, okay, in the next iteration I will say I will allow one, at most one number of edge between I to j. So in this case if I draw the same thing over here, I j, then in this case if there is a direct edge between I to j, if there is an edge, then in this case whatever is the weight of ij, that will become your shortest path because it is better than the infinity. So in this case I can say delta ij is equals to wij. Okay, this is the best case when m is equals to 1. When we allow one more uh, edge, that means m is equals to 2. If I write the allowed set, initially it was 0, then 1 allowed vertex already found best path, and we are allowing one more edge. So in this case I have a direct edge which is taking me I to j and its weight is wij, and currently this seems to be the best shortest path between I to j. Then in this case instead I have this option available with me, and it is wij, and in this case I am using at most m minus 1. Let's say this is our old path. Now if I allow one more edge, that means what? That I can have one more edge allowed to go. So in this case I can do, what I can do is I can add new k's over here, which will take me from k to j, because these are the new edges which are allowed, and I can integrate all those k's over here. They will take me from k to j. Now as you know that I have only, this is by using this. So in this case I am only allowed to use one edge which is left for this path from I to k, right? So if this is using your mth uh, edge, then this altogether it will be m. So whatever is the current value of the m. So that means if I now m becomes 3. So in this case whatever is the best we will pick, it can be either taking that means this is our old path, or the new path in which we have a detour using some node k. So when m is equals to 3, what will happen? I will have all the possibilities from I to j. The old path which is using, in this case m is equals old path, this is your old path, old best path, and now I will take a k and I will try to improve upon it by using different possibilities and connecting it with j's, and in this case I will have m minus, this will use m minus 1, m minus 1, m minus 1, and the mth edge will be used over here. So this is how it will be done. So remember that whenever I have used, for example in this case your m minus 1 is 1, in this case m minus 1 is 2, and so on and so forth. So all we are trying to do is remember that once we have solved this part, now if we have, once we have solved this subproblem optimally, we can reuse it in the while solving rest of the subproblems. So in this case, if and why is that? Because if we remember that shortest path problem has optimal substructure and overlapping subproblems. We have discussed that already. So that means because of this, I can say that once I have calculated the best shortest path for m-1, at most m-1 edges, I can reuse it, and I will just see that by adding a one more edge, which is your mth edge, to your path, is there any improvement or not. If there is any improvement, then I will stick with that, otherwise I will keep on improving. So let's say if I remember Dij, this is the same Dij which I mentioned a minute ago over there, that means the capital D. So in this case, I will improve upon it, and I will change it, and I will use a superscript m. There is m means the at most number of allowed edges. So in this case, I will try to find out the dynamic programming based solution. That means there has to be some kind of a recursive call in which I have two possibilities. I have to take the minimum of, but I have two possibilities, whether I will stick with my old solution, old best path, which is taking only m-1 edges, or I will use Dik plus an additional direct edge from k to j, and see whichever is the smallest one, we will pick as the shortest path. So this is the dynamic programming variant of this problem, which can be used to solve this problem. So this is what we have discussed in our last lecture, and today we'll see that what is the time complexity of this algorithm. In short, we want to say that is there any improvement from big O of V4, which was the time complexity of solving this problem using Bellman-Ford. So this is what we have to. Okay, I want to highlight one more thing over here, which is that Dij, whenever we are using n-1, because this is the maximum number of edges I can have. n-1 is the maximum number of edges I can have between I to j. This n-1 is the maximum number of edges I can have with n vertices. No cycle allowed, right? So if this is the case, this is the n-1. So Dij n-1 means that I have to find the shortest path between I to j by using at most n-1 edges. So remember that this is our final solution which we want to calculate, right? So this will give us the Dij, which should be the final value in our matrix. So if I try to solve Dijn, so that means what? We are trying to say that, okay, I will try to find the shortest path between I to j by using at most n number of edges. So remember that there will not be a n unique edges unless there is some kind of a repetition in the edges. So if we allow n, that means there are two possibilities. What? When we say Dijn, that means repetition of edges are allowed, and remember that n minus 1 are the n minus 1 are the unique number of edges between I to j, and they are the maximum number. So if we go towards n, there, that means repetition is allowed. If repetition is generating a cycle, which of course it does, and cycle of positive weight, then it will never be picked by Bellman-Ford, because I can always find a better path by removing this cycle from my path. But this that means Dijn will only improve if cycle has negative weight. That means there is a negative weight cycle in the graph, and shortest path does not exist. Okay? So this is important. So in that case, if there is no negative weight cycle, then Dijn minus 1 will be same as Dijn. This will be same as Dijn plus 1, and so on. Why is that? Because if you are allowing more and more edges, yes, you are allowing it, but adding those edges will not have any positive impact on the shortest path, then we will never go towards it. Remember that superscript n means we are talking about at most. We are not forcing it that it has to use n, rather we are saying that you have option of using from 1 till n. So keep that in mind. So whenever we are talking about from n minus 1 onwards, so that means we are talking about some repetition of edges. We are saying, okay, you can repeat one edge, you can repeat two edges, you can repeat three edges. So in that case, if we are allowing that, so that means we can always find a better path by not using it if it is generating a positive value in the shortest path. Now let's come to the time complexity of this algorithm. Okay, to calculate the calculate the time complexity of this algorithm, let's talk about simple matrix multiplication. Okay, you can ask why we are talking about matrix multiplication. basic reason behind it is, what we are trying to do is we are trying to see that what is the parallel, is there any kind of a similarity between the number of computations or operations, the algorithm which we have discussed right now above. Is there any kind of similarity between these two? If there is, that means if number of computations, number of steps are same in both the cases, then in this case we can say that the time complexity of matrix multiplication will be same as the time complexity of the above algorithm. So we do not have to go further than that. That will be enough to prove that the time complexity of the above dynamic programming based approach will be what. Okay, so in this case we know that simple matrix multiplication Cij between C is the final matrix. It is A matrix multiplied by B matrix will be this one, right? So in this case we already know the time complexity of a simple matrix multiplication is big O of n cube. So where n is the number of entries. So we are, let's say for the sake of discussion, let's talk about, we are talking about n by n matrices, n by n, n by n, n by n. So in this case total time complexity to multiply it will be big O of n cube. What if we map the plus to min and the multiplication to plus? What will happen? So in this case Cij will become min of all the possible k's, Aik plus Bkj. Remember? So in this case remember that this multiplication will be mapped to plus, and this multiplication will be mapped to min. So that this is the new transformation. So instead, now initially we were calculating C is equals to A dot B. Now by this new mapping, let's call it a new funny multiplication, and now we say C is equals to A sum this new multiplication B. Remember that. See? So in this case this B is this one, this A is this one. So as you remember that this actually represents the I, this is your J, and this Ik actually represents the shortest path which we have calculated for all different k's, and then there is a direct links between k to j. Okay, so in this case how many possibilities of k's are there? That means all the vertices can be considered. Remember? Okay, so that makes sense because we are allowing k, so we can pick any vertex over here and see that if there is a direct link between k or j or not. If it is, then see if it improves our path or not. So that means what? If we look at only this path, only on this portion, this represents what? It represents the direct edge weights of the graph. Remember that we are talking about the direct edges. So have we defined this direct edge weight somewhere? So let's look back. If you remember that we have defined a direct edge weight matrix somewhere over here. It is over here. There you go. Remember that. Okay, so this is what we have defined. So that means what? So in this case, if this is the capital W. So then in this case we are talking about this funny multiplication with the W, where this A is the already found path from I to K, which is represented by what? dm minus 1, and this C is your new improved path if there is some kind of a improvement which we have found. So this is the transformation of the old or the simple matrix multiplication into a new form. So this means what? That whenever I have to calculate dm, I have to multiply this funny multiplication which we have defined right now with a W matrix with the already computed the path weight. So let's see, can we define an identity matrix for this new multiplication? Remember that in simple multiplication, I is equals to what? I is equals to 1 0 0 0 1 0 0 0 1 and so on, right? And remember that whenever we are performing a multiplication operation, there are only two operations. Operations are plus and multiplication. Okay, so remember that this one correspond to the identity of this multiplication, and this 0 represents the identity with respect to this plus operation. So over here we have transformed plus into min and dot into plus. So let's change the identity matrix change the identity operations accordingly. So the operation for plus to min, now identity operation or not identity value is infinity. Why is that? Remember that when we are talking about plus, that means some x, when it is plus with a 0, it will result in the same value. That means for the plus operation. So when we have transformed plus into min, we have to use some min and x, and we have to have some identity value. Whenever we perform that, it should return x. So we can see that there are only possibility over here is infinity. Whenever we take the minimum of x and infinity, and every value is smaller than the infinity, that is why we'll get an x. So that means whenever or wherever we have identity value 0, we have to transform into an infinity. And second thing is dot of x, when multiplied by 1, that will result the same value. So identity value for multiplication is 1. So but we have transformed a dot into a plus. So same, we know that in this case I have to transform 1 into 0 to get the same value. So these are the new transformations. So in this case, if I have to define a identity matrix for this operation, so in this case instead of 1 I will use a 0. So wherever we have a 1 we will use 0, and wherever we have a 0 we will use infinity. So infinity, 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 0, infinity, and in 0 is infinity, infinity, and 0. So this is the identity matrix for this new multiplication operation. So that means what? So that means that whenever I perform some matrix, let's call it M, this new multiplication with this Ix, this will return M. Okay, so this is the definition of a identity matrix. If you look at closely, this actually represents a familiar thing. Do you remember that we talked about a base case D0? D0 means what? That I am talking about the shortest path between I to j without using any intermediate edge. So this is same as calculating dij 0, and if you remember, this means what? If we have I is equals to j, then delta ij is equals to 0, and if I is not is equals to j, then delta ij is equals to infinity, right? So this is what we have calculated. If you look at this matrix now, so what it shows, Ix actually represents, in this case, this 0 0 means delta I, remember, and rest all are delta ij, then delta ij, then again this is delta ii, then delta ij, and so on, right? So in this case, this is as per this definition always 0, and as per this definition it is always infinity. So this will transform into very same thing. So that means this is equals to d of 0. So by looking at this expression again, I can say that d of 1 now is equals to d of m minus 1, which is 0, with a new multiplication of w. Okay, so this is your identity. So that means by multiplying it with w, d1 should be same as the edge weights matrix, which we have defined before. Okay, if I want to calculate d2, this is equals to what? d1, this funny multiplication multiplied by another w. So this is equals to w because of this. So that means d of 2 is equals to w, this funny multiplication w. Similarly, d of 3 is, again, I will call it w square. And remember that when we are talking about square, we are talking about 2 times this operation. Okay? Or no, not 2 times. It means that this funny multiplication between the same w's. And when we're talking about d3, d3 is equals to d2 multiply by this funny multiply by w, which d2 is w square multiply by this w will result w3. So you can see that there is a state of a pattern, and the final value which we wanted to calculate was dn minus 1. So dn minus 1, by looking at this pattern, should be is equals to wn minus 1. Multiplied by the time required to calculate this multiplication. So that means it turns out to be big O of n4. So that means it is no better than simple Bellman-Ford, which we have applied before, because it was also the same big O of V4. Remember that? So that means it is no better than the previous case. But with very small tweak additional, so we can improve upon it. Remember that whenever we are talking about A4, that means, or not A4, okay, let me, whenever we're talking about V4 is equals to V square multiplied by V square. Okay, so instead of using, that means we can, instead of using simple jump, because we need to calculate, let's say Wn minus 1. For the sake of discussion, let's say we want to calculate W10. Okay, so in this case I have to make how many? 10 multiplications. 10 multiplications. In this case we are talking about our special type of multiplications. Nevertheless, all these multiplication will again take the very same time as the normal matrix multiplication. So but it will be 10. But let's say instead of, because we want to calculate W10, let's say by multiplying first two W's, I get W square, right? Now instead of multiplying it with another W, I will multiply these two W's again together. So I will get W4. Okay, so this is one multiplication, this is second multiplication. In the next iteration, instead of multiplying it with again W2, I will multiply these W4s together. W4 multiplied by W4, I will get W8. Okay, but we wanted to calculate W10, remember that. So instead of multiplying it with another W8, with W4, I will say I will multiply it with another W8 multiplied by W8, or you can also go for W2 because we have already calculated that. But let's say for the sake of discussion it is W16 now. So altogether how many calculations are required, how many multiplications are required? 1, 2, 3 and 4. So 4 multiplications are required. Okay, so in this case there is a huge improvement. Not huge, I would say that depending upon the size of the matrices it can be huge, but there is an improvement for sure, because we are going from 1 till n, and jump size doubles every time. So that means how many jumps are required to go from 1 till n if your jump size increases double? So that means we need log of n minus 1 jumps. So that means all together we have to calculate first W square, then W4, then so on up till W 2 of log of n minus 1. Okay, so if we are talking about log 10, so in this case you can very easily calculate that how many times we have to calculate that. Okay, you can say that, okay, over here you are saying that I want to calculate W10, but over here you are calculating W16. So is it okay? Because instead of calculating W10 you are calculating W16 to find the shortest path. Is it the same thing? Yes, it is the same thing, because as we discussed before that if you want to calculate dm n minus 1, this is same as dn, this is same as dn plus 1, and this is same as dn plus 2, and so on, provided there is no negative weight cycle. Okay, but so because of this very reason we can say that instead of calculating W10, if you instead of calculating W10, if we calculate the even higher powers, that means 11, 12, 13, 14 and so on, so it will not have any detrimental impact on the shortest path. Rather the answer will remain same, provided we have the same we have the power greater than the desired power. But now question is how we can detect, maybe if you have calculated W16, it is improving upon W10. How we can ensure that? The simple check is, once we have the values, then in this case whatever we have in the diagonal that represents 1 1 2 2 3 3 so on up till n. Remember, all these represents cycles, or we can say that what is the what is the cost of going from I1 to J1, right? So going back to the same thing, because this is what is cycle. So in this case, if any of the diagonal value is negative, that means we have negative weight cycle in the graph. And how much time is required to look at the diagonal of a matrix of size n by n? It will be a simple linear loop which will take big O of n time. So altogether, if you look at this algorithm, so instead of making, if you remember that previously what we are saying, that n cube was the time of the first multiplication, and that was multiplied by n, where n represents the number of multiplications required. But in this case, in our current case, we have reduced from n to log n. So that means with this new hack, my new time complexity will be big O of n cube log n, which is of course better than n raised to power 4. So we have improved our previous case a bit. That means we have reduced n4 to n cube log n. I will stop this video right now, and in the next video I will discuss Floyd-Warshall algorithm, which is even better than this approach, and it still uses the dynamic programming to find the shortest path.